It's a pleasure to be here again. And today I will talk about mathematical truth. And the structure of the talk will be, it'll have 4 parts: truth in general, truth in mathematics, solutions to problems, and relations to other philosophers. Now, truth in general. Today, at least in the United States, the most popular or common view of truth is deflationism. And there are many versions of deflationism, but the way I will treat it is deflationism says, first, the truth is a trivial notion, that it has no hidden structure awaiting our discovery. This is citation from Horwich. That there is nothing deep about it. The truth is nothing more than this quotation, a true P if and only if P, and its only importance is technical. It enables us to express things that it would be difficult for us to express otherwise. For example, suppose we want to affirm Einstein's theory of relativity, but we just don't know all the details of the theory. We cannot state all the theorems or principles of the theory, so we just say Einstein's theory is true. Or we want to approve of the law of excluded middle. There are infinitely many instances. We cannot state all of them. For that reason, we can use semantic assent and say every sentence of the form P or not P is true. Now, my own approach is very different, and it is a substantivist approach. I talked about it a little bit yesterday, but I'll say a few more words. The main idea is that the topic of truth is a deep, rich, complex, and informative topic, central to philosophy. And second, it both yields itself and requires deep explanatory, informative, philosophical theory. Now, my starting point is a set of observations which I call the basic human cognitive situation. I also briefly mentioned it yesterday. And it is based on 5 simple observations. We live in a world of which we are a part. We desire to know and understand this world, not just practically, but also theoretically. But our cognitive resources are significantly limited, and this renders the world highly complex relative to our epistemic abilities. Nevertheless, we humans are ambitious creatures, and we aspire to know the world in its full complexity. What makes our aspiration possibly achievable? The circumstance that, although we are cognitively limited in significant ways, we also have significant cognitive resources, including innate and acquired cognitive abilities, and I think this is very important, the capacity to actively manage our quest for knowledge, design experiments, build various tools, and so on. Given our desire to know the world in its full complexity on the one hand, and our susceptibility to error on the other, we need a standard that will guide us in developing theories of the world. Truth is such a standard. It is a standard of correctness for statements and theories. Standard is the same for me as a norm. This standard is satisfied by a given statement theory if and only if whatever it says about its subject matter, some facet of the world, holds in the world of this facet. So now, truth as a correspondence standard. It follows from the above considerations that truth is a correspondence standard. But what kind of correspondence? Is it copy, mirror, isomorphism? Probably not. Why? We have to go back to the basic human epistemic situation. On the one hand, we have a complex world. That means that it probably requires complex cognitive roots in order to reach it. Second, we have a complex mind. That means that we have the ability to forge complex cognitive roots to the world. And three, given that there is also a complex world and a complex mind, we need to allow complex roots or patterns of correspondence, multiple roots of correspondence, including indirect roots. And so one way to look at it is pluralism of forms of correspondence. What is the guiding principle in deciding what standard of truth is suitable for a given field of knowledge? My own view is that it is the Wittgensteinian saying, look and see. Don't assume in advance the truth is a copy of reality or isomorphism with reality, but look and see. Look and see how physical, biological, psychological, mathematical statements and theories are connected to reality. So, from my point of view, for the truth theorist, it is a process of discovery. What is mathematical truth? How truth works in mathematics. This leads us to the second part, truth in mathematics. My approach to truth in mathematics differs from the usual approach. Usually, philosophers start with the language of mathematics. Take arithmetic, for example. The language of arithmetic treats numbers as individuals. It uses individual constants or singular terms, more generally, terms of level 0, to refer to numbers. So to say that number statements are true in the correspondence sense is to be committed to the reality of numbers, that is, numerical individuals. But it's hard to find numbers in the world. Numerical individuals hard to find. So this leads to the well-known problems of Platonism. Two worlds, a Platonic world, our world, numbers are there and we are here. My approach is different. My starting point is not language, but the world itself. My first question is there anything in the world for mathematics to be true of? Is there anything in the world, objects, properties, structures, or anything else, such that to obtain knowledge of the world, we need to develop a discipline like mathematics in order to study this thing? And the question, is there such a thing in the world? And my answer is yes. Mathematics and the world. My initial observation is that objects in the world in general have properties of various kinds, physical, biological, psychological, and so on. The question is, do they have formal properties, that is, properties that require a discipline like mathematics in order to study them? What are formal properties? Speaking very generally, I would say that they are structural properties. They are sensitive to patterns, not to who the individuals are. For example, identity, a first level relation, is sensitive to this pattern. When we have this pattern, we have identity. Two, the second level cardinality property is sensitive to sets of different things. And so it has to have sets of different things. They are the kind of sets or properties that have cardinality 2. So each such property is sensitive to some pattern. It doesn't care what the particular individuals here and here are. So, do objects in the world have formal properties? Let's start with ourselves, people in this room. Do we and our properties have formal features? The answer appears to be yes. Each one of us has the formal property of self-identity. That's part of the properties we have, in the same way that we have a property of being a person, of being a man or a woman, and so on. We have the property of being self-identical. Now, let's take a property that we all have in addition to that self-identity, and this is the property of being a person in this room. This is a very simple property. Everyone will accept this kind of property. This kind of property also has a formal feature. It has the second level formal property of cardinality. For example, more than 10. This is part of the reality of this room, that there are more than 10 people here, in the same way that it's part of its reality that there are tables here and chairs and people and so on. Now take a first level relation that we all have to each other, actually besides me. X sits next to Y. This relation, also very simple relation, part of the reality of this room, has the second level formal properties of symmetry and non-transitivity. Going on, let's take two of my own first level properties. X is a speaker and X is a woman. These properties are also subject to many formal operations. For example, complementation, X is not a speaker. Intersection, X is both a woman and a speaker, and so on. So again, we see that the reality, very simple reality of something as simple as this room, involves already so many formal properties. And I would like to say that this is the basis or the starting point of mathematics, because what we want to know is the laws that govern all these properties. And for this, we need something like mathematics. So, but if these formal properties are real, part of the reality of this room, then it is reasonable to presume that they exhibit regularities or governed by laws. And we, the ambitious creatures that we are, want to know these laws. Which discipline studies these laws? A reasonable answer is mathematics. But does mathematics fit this job description? Suppose not. That would be quite absurd. It would be quite absurd if mathematicians want to know the world. They know that there are cardinality properties in the world, but they study different cardinalities, imaginary cardinalities, conventional cardinalities, inventions of the mind. That would be very strange. So I think, given that the subject matter of mathematics are properties that are part of our reality, it is reasonable to think that mathematics as a discipline study, maybe along with other things that it does, the laws that govern these properties. Another possible objection to my approach might be that only applied mathematics, not pure mathematics, has to do with the world. My answer is, 1, A, applied mathematics being applied requires a non-applied mathematics in order to apply it. What does it apply? What does it apply? It applies something which is non-applicational, something which is theoretical. 2, the task of formulating the laws governing the real formal properties in complete generality and systematicity requires something on the order of pure mathematics. And I will explain this a little later in slide 27. So that I would like to say that given that what we want is to understand and to know the laws that govern cardinalities and other formal properties in the world in full generality, we need something like pure mathematics. But here we come upon a puzzle. As we have seen, most of my examples besides identity were examples of second-level properties as formal properties. But mathematics, arithmetic, set theory are done today on the first level. They are first-level theories or first-order theories. So the puzzle is, if the formal is largely second level, why is much of mathematics first level or first order? Now, let me try to answer this question, this objection. First, the main issue is it possible in principle to account for second-level phenomena by first-order theories? And the answer to this is yes, so long as constraints of accuracy and consistency are satisfied. That is, we already clarified that we can reach reality in many ways, in complex ways. Given our limitations, it may be more convenient or more suitable for us to reach it through first-level theories, even though the aspects of reality we would like to reach are second level. How or why would we need first-order theories? One possible conjecture is that humans are better in cognizing individuals and their properties than properties and their properties. So humans are doing better cognitively when they think about things in terms of structures of individuals and their properties rather than structures of properties and their properties and their properties and so on. They or we get confused when we talk about properties of properties, but we see things intuitively more clearly when we think in terms of individuals and their properties. So we posit an ontology of mathematical individuals that represent formal properties. How would we do that? We use what I call composite reference and truth. And this is what I mean by that. Here we have composite reference. So usually we think in terms of simple reference. In simple reference, we have two levels. We have reality and language. In reality, we have individuals of level 0, say we think the common view is the individual one. And in the language, we have a singular term of level 0, the numeral 1. In the world, we have properties of level 1, even. And in the language, we have predicates of level 1, even. But this is a very simplistic way of looking at the language of mathematics. If in the world what we have is formal properties, then what we need is a more complex root of reference, a composite root of reference. We have the second level properties, say the cardinality property 1 and level 3 even. Then we posit individuals of level 0, the number 1, and properties of level 1, the property even. And then in the language, we use names of level 0, the numeral 1, and predicates of level 1, the predicate even. And now the way the root of reference goes is from first level vocabulary to first level posits to second level properties in the world, objects in the world. And at least in principle, there is no reason why the root of reference for humans who want to know the world and what they want to know is second level formal properties would not take this way. Once we go to correspondence, to truth, we have a similar thing. Take the two sentences, 2 plus 7 is 9, and for every m and n, m plus n equals n plus m. One is true if and only if, on the level of posits, addition applied to the posits 2 and 7 gives us 9. If and only if, in the world, this joint union of the cardinality properties 2 and 7 is 9. And this is the second level traditional formalization of this. 2 is true if and only if, at the level of posits, the operation of addition is symmetric. If and only if, at the level of the world, this joint union is symmetric. Yeah.
What I don't understand, why you call this talk about sets, you attribute to the world, and talks about numbers, you attribute, say, to language.
Okay. That's a good question. What I'm really talking about in the world are properties. And I'm borrowing the language of set theory to talk about formal relations between properties. So I could have used a different terminology, but I would like to make to use terminology which is familiar to us, so I'm using set theoretical terminology, but I could have, taken a whole hour and invented, new vocabulary to talk about properties, which is formal properties, which is different from the vocabulary of set theory. But that would be just a technical thing that would take too much of our time. And but I should have indicated that. Thanks. Okay, there is much more to say about composite correspondence in mathematics, but two of its advantages are, one, it gives, I think, a genuine explanatory account of mathematical truth correspondence, which tells you what in the world mathematical statements correspond to. They correspond to formal laws that govern formal properties. Second, and this is what we will turn to now, they provide solutions. This approach provides solutions to problems with the traditional conception of mathematical truth and mathematical realism. Okay, so now I will go over a few problems, and I will show how my approach enables us to quite simply solve these problems. So first, let's take the famous identity problem from Benacerraf. So the problem is, what is the number 2 in the world? Which thing is the number 2? So we have Zermelo's 2 in set theory. Now I'm talking about set theory, which is the set of the empty set. And we have von Neumann's 2, which is the set of the empty set and the set of the empty set. And the question is, which is the real 2, if any of these? From my perspective, there's no problem. These are simply two different but equally good posits that represent the cardinality property 2. So there's no reason why there should be just one system of posits that represent certain formal properties, and set theory enables us to have two systems that represent cardinality properties in somewhat different ways, but they are just as good as each other. That is different but equally good representations of the second level property 2. Oh, this seems to jump. The application problem. Wigner, Steiner, and many others. So this is the question: how is it that mathematics applies to the physical world? If we are Platonists, this is a very difficult question to answer. But in my approach, it's very simple. This is completely straightforward. Physical objects have abstract properties, that is, formal properties, as we have just seen, and stand in abstract relations. Therefore, it is not surprising that the laws that govern these abstract properties and relations are applicable to physical objects. Okay, mathematics starts from the world that physics starts from, and so it's not surprising that mathematics applies to the physical world. I should just maybe mention again, to prevent a misunderstanding, when I talk about properties, I use the word property for relations, for properties, proper properties, for functions, for all these things. 3. The necessity of mathematics problem. The problem is that the problem for correspondence theory of truth for mathematics is, or one problem is, that if mathematical truth is truth about the world, then many people will say a truth about the world is contingent. So mathematical truth would have to be contingent. Now, on my view, this is not the case, and I will talk about this in much more detail in the formal philosophy conference in my talk about invariance, but I'll briefly explain it here too. Mathematical truth is truth about formal laws governing the world, and it depends on the nature of formality whether these laws are necessary or not. So what we need to know is whether formality involves necessity, whether formal property, because they are formal, have laws which are necessary. On my account, formal properties and laws are characterized by the fact that they pay attention only to patterns, not to the and they do not distinguish between individuals. As we saw in the case of identity, take any individual, it's identical to itself. It doesn't matter if it's me or you or she or he. Identity does not notice. Similarly, cardinality. Take the people in the first row, I think there's maybe the same number is in the second row, then cardinality doesn't distinguish between whether we talk about these people or those people, about the tables or those tables, and so on. So formal properties simply do not distinguish between individuals. They don't notice replacement of individuals. They are invariant under all one-to-one and onto replacements of individuals. Again, using set theoretical terminology, we can say that formality is invariance under isomorphism. Isomorphisms. A property P is formal if and only if it is invariant under all isomorphisms. Let me give you an example. Let the structure AB be a structure of objects where A is its domain and B is the extension of some property in the domain, a subset of the domain. Now, cardinality property are formal. What does that mean? It means that if the structures AB and A prime, B prime are isomorphic, then cardinality properties don't distinguish between them. The cardinality of B in the first structure is identical to the cardinality of B prime in the second structure. And this holds regardless of whether the structures AB and, A prime, B prime are actual or counterfactual. If I think about counterfactual individuals that could sit here instead of the people in the first row, they would also have the same cardinality as the actual individuals in the second row. So mathematical formal properties are indifferent, don't distinguish between actual and counterfactual individuals, actual and counterfactual structures, so long that they are isomorphic. But if formal properties do not distinguish between an actual structure and a counterfactual structure isomorphic to it, then their laws, formal laws or mathematical laws, cannot distinguish between such structures either. That is, if they hold of any actual structure, they also hold of all counterfactual structures isomorphic to it. For example, the laws of cardinality apply to all physical objects, actual and counterfactual alike. And therefore, the laws of cardinality apply in all counterfactual and actual situations. And that means that they are highly necessary. And the same holds for all mathematical laws, laws governing formal properties. In this way, our account of mathematical truth solves the problem of mathematical necessity, the necessity of mathematical laws. And I will say just briefly that I think generally the notion of invariance is a very fruitful and important and informative notion, and I think that it can be used to explain, to solve this problem in the spirit of my proposal. For the large ontology problem, this problem is the large ontology of mathematical individuals. If I start with the world, someone might say, well, the world maybe has only finitely many individuals, but mathematics has higher and higher infinities of cardinalities of higher and higher infinities. So how do we get to that from the actual world? So my solution is this is not the problem if the individuals are posits. Question, why do we need a large posited ontology? Answer, this is required in order to represent the formal laws in their full generality and modal force. Let me give two examples. One, to express the laws of natural numbers in their full generality, we need to posit something of the order of a denumerable ontology of individuals. That is, we cannot express the laws of number in their full generality if we assume just a finite number of posited individuals. And so this is how we get to the ontology, full ontology of arithmetic. Now, two, once we use a denumerable ontology of individuals to express the law of power set or power property, cardinality, that is the cardinality of the power set of the property alpha is larger than the cardinality of the property alpha, in complete generality, we need to posit something on the order of indenumerable ontology of individual. So that's how, in order to start by explaining the laws of cardinality when we are talking on the level of the world, because cardinalities are so special, they are formal, their laws have to be extremely general, and we need to explain it by using something like a very large ontology. Considerations of this kind explain the large ontology of, say, set theory up to L. What about beyond L? This is an open question from my perspective. One way to look at it, we may view the set theoretic hierarchy as ending in L. Some people would say that. Or we may view it as extending beyond L. Concerning two, there are several possibilities. One, to determine truth about sets up to L, for example, the truth value of the continuum hypothesis or the generalized continuum hypothesis, we have to go beyond L. Second, to find out truth about all possible formal structures, we have to go beyond L. So there are ways to see that we need to go beyond L, but it's also possible that we'll find out that actually we don't have to go beyond L. Again, in the spirit of look and see, this is for me an open question. The last problem, the cognitive access problem, again by Benasraf. The problem is, how can humans access cognitively the formal or mathematical features of reality and the laws governing them? Now, this is a problem for both Platonists, who have to explain the access from one reality to another, and for radical empiricists who limit cognitive access to causal patterns. But it is not a problem for us. And on our approach, objects in the world, the one and only world, have both physical and formal properties, so there's no question of having to access another Platonic world. Two, on our approach, intellect can play a role in knowledge in cooperation with and alongside with sensory perception. There is no reason why we limit knowledge only to sensory perceptions. Humans, on my view, use all their cognitive resources to reach the world cognitively. And this includes intellect that expands our cognitive reach beyond what radical empiricists allow. I wrote quite a lot about it, but I cannot talk about it here, but it appears in my book, Epistemic Friction, an Essay on Knowledge, Truth, and Logic, 2016. Okay, the fourth and last part of the talk, relation of the present conception of mathematics to other philosophical views. I will start with Aristotle, and the citation is from the Jonathan Lear translation. There is quite some similarities between my view and Aristotle's, in the sense that we both start with the world, or that, like Aristotle, I start with the world. Obviously, Aristotle says physical bodies contain surfaces, volumes, lines, and points. And these are the subject matter of mathematics. The mathematician separates them, for in thought they are separable from motion, and it makes no difference, nor does any falsity result if they are separated. That is, in order for us humans to study them, these aspects of things, we have to cognitively separate them from other aspects. And the best way of studying such features would be to separate and posit. He uses the word posit, what is not separate in reality as the mathematician does and the geometer. And Jonathan Lear clarifies this. For Aristotle, mathematics is true not in virtue of the existence of separate mathematical objects to which its terms refer, but because it accurately describes the structural properties and relations which actual physical individual objects do have. Frege. Similarities. 1, cardinalities are second-level properties. It's a Fregean theme. Mathematics is objective, and there's a close relation between logic and mathematics, but this I will not talk about today. Differences. Frege puts much more weight on language as a key to ontology than I do. For Frege, mathematical truth is analytic in the traditional sense. For me, it's not. It's factual. For Frege, truth is unanalyzable, primitive. For me, it is analyzable. It is explainable. And for Frege, different relation between logic and mathematics. Again, I won't get to it. Maybe tomorrow I'll talk a little bit about it. Quine, similarities. Positing objects is central to human knowledge. Posits are not ipso facto unreal. And relational holism, his approach is holistic. I call my approach foundational holism, and there are some similarities. Differences. Quine, all objects are posits. For me, not all objects are posits. Quine, role of posits is purely pragmatic. For me, it's not purely pragmatic. It's a representation of something real. For Quine, mathematics' only role is service for science, indispensability. For me, mathematics is first and foremost an attempt to study the formal structure of the world. And for Quine, sometimes advocates a one-unit holism that I don't. Quine sometimes says that the smallest unit of epistemic significance is the whole of knowledge, and for me, this is not correct. In order to know things, we need structure. We cannot just treat everything as a one blob. Finally, the fictionalists, especially Hartree-Field, similarities. Theories do not need to refer to real objects in order to be good. Rejection of Platonism and appreciation of creativity in knowledge. Differences. For Field, mathematical theories are false, and for me, they are potentially or usually true. If you know how to connect them to reality, on my view, the laws of mathematics are correct. They are true, they are not false. And Field has no interest in mathematics aside from science, while I do. Conclusion. Mathematical truth, on my view, is composite correspondence. Correspondence with the formal layer of reality. This has interesting connections with the literature and has several advantages. One is it provides a substantive account of mathematical truth, a mathematical correspondence without either Platonism or radical empiricism, and solution to outstanding problems in the philosophy of mathematics, the identity problem, application problem, necessity or modal force problem, large ontology problem, and cognitive access problem. Thank you.
Thank you very much for a nice talk. It's time
for question discussion. Please raise your hand, I will give you a mic. Andrei.
Thank you very much for very interesting talk. No, I have a lot of questions, but actually it's really question better understand your position. So if I understood correctly, what you call posit is still kind of ontologically grounded. So it has behind it like real existence, unlike, say, Quine. And so now question is, and also if I understood correctly, you correct me, your idea is actually it's close to Aristotle, that posits are kind of you put on zero level, individual level, what is ontologically is a property.
Right.
It's very close to Aristotle. But then there are actually standard kind of difficulties of this position. And so could you probably just illustrate it, not even beyond L or something, but even with big numbers, right? We very easily, if we write some like 10 to 80s, by best of physical knowledge is already beyond what physically exists, and still we can, of course, make simple mathematical truths, state, prove simple mathematical truths. So how this mechanism works, just in case of 10 to 80 or something?
Yeah. So the way I look at it is the following. We want to understand the principle, the structure of cardinalities. And we start from finite cardinalities. And we have 0, 1, 2, something like this, that actually we find them properties in the world that have these cardinalities. But these properties are formal properties, and they have a very strong degree of invariance. And in order to understand how the structure of this property, what is the structure of these properties, we cannot stop it in, for example, the number 1000. Because if there were another thing in the world, then the same cardinality, the same principle will hold. Cardinalities, formal properties, don't distinguish between what actually there is in the world and what could have been in the world. And for that reason, in order to understand the principle, we have to treat it. We cannot stop. We will not understand it correctly. We will not have a genuine understanding of the principle of the generation of natural numbers if we stopped at a particular number. The possibility of adding 1 has no end, and we require it in order to understand how the principle of cardinalities.
That's kind of strange, and this is epistemic argument, right? So it's not ontological. Why not? I mean, why, if it's matter of fact, right, that, say, there is no bigger number than something, let's say number 10 to 80 or something doesn't exist, right? It's a fact of the matter. So what is the epistemic reason to posit it? And that's not a kind of... so it's kind of epistemic part of your argument.
It's both epistemic and metaphysical. It is because the formal properties themselves do not distinguish between what there is and what could be, that formal properties do not end with what there actually is. And maybe that's a difference from Aristotle here. But I think Aristotle, I don't think that he had a theory of the significance of formality. We have to understand the special significance of formality in order to know why. To understand it, we have to go beyond actual individuals and actual properties. And I will say also that this is something that we find also in physics, for example, and everywhere. Suppose, for example, that things developed in the world in such a way that a certain combination of chemical elements did not exist in the world. That does not mean that the chemist does not want to understand these chemical combinations and find out things about them. The chemist also does not stop with what there is. Similarly, even in physics, for example, say, take the law of gravity. The law of gravity does not stop with the objects that actually exist in the world. Suppose that Earth had 2 moons or had a different moon from the one it has. In order to understand gravity in full generality, we have to understand that it applies to that thing too, even though it does not actually exist in the world. And so I think that both metaphysically and epistemologically, things that have a higher degree of invariance, things that are formal, have to go beyond, in principle, beyond what is actual. And from the point of view of knowledge, if we want to understand the principles that govern them in full generality, we ourselves have to think about them as holding about the full array of properties or objects they could hold of, and not just those that actually exist.
And you are not model realist. So when you say could, it's without ontological commitment, right?
It's not ontological commitment to our world, right?
Okay, Ilya?
Yeah, the question about how to make sense of parts of mathematics other than arithmetic on this approach that focuses on this kind of structural properties. I mean, to take just the simplest possible extension, the one to negative numbers. I mean, I can see that once you have set theory, you can model in the set theory the negative numbers. But it's I'm wondering more about whether this can be interpreted as corresponding to formal properties in the world in the same nice way that you explain for natural numbers, because it's not obvious to me what they correspond to. So I don't just.
An example which is very simple, and with the negative numbers it will be more complicated, but there are phenomena in the world that are also naturally describable by thinking about negative numbers. For example, you have a starting point, you go one direction, the other direction, and you can indicate it by negative numbers and positive numbers and many other phenomena. Again, it will not be, the connection will not be as simple and direct, but there is a connection, and when we talk, we use negative numbers in order to say things about the world, and they reflect certain features of the world. But there is another aspect that I didn't talk about at all, and this is something like group theory. For example, about arithmetic, there is a sense in which we can say that it's true or false. And similarly about set theory. We can say, well, a given set theory is true, or a given set theory is false, or we can wonder about it, or we want to establish its truth or falsehood. But there are some mathematical theories like algebras that are, it's hard to say that group theory is true. But I think these also fit in nicely in my approach, because what happens there is, because the world has formal features, there are formal structures in the world that we can represent in various formal, pure formal ways. And algebras, various algebras are used for this purpose. So algebras create formal models that are applicable to real things in the world. And I think Stuart Shapiro had this distinction between mathematical theory like arithmetic and set theory, which can be said in a strong sense to be true or false, and other theories that provide models that can be used in the world.
Thanks a lot, Gila. Okay, and my question concerns logic more than mathematics. Logic as formal ontology deals with formal properties and turns them to the laws of deduction. So if we consider invariance under isomorphism or under permutation in particular, as a criterion for mathematics, is it possible to distinguish between logic and mathematics? It's an obvious question, it seems to me.
Something that I'll also talk about it tomorrow, but let me just say briefly that in my view, both mathematics and logic deal with the formal. And in this way, it is somewhat close to Frege's logicism. But it differs from Frege's logicism because I don't identify logic and mathematics, and I don't reduce one of them to the other. I think that logic and mathematics are doing different things with the formal. In mathematics, we study the formal. We want to know whether, for example, the continuum hypothesis is true. We want to know, we wanted some, people spent a lot of time trying to find out whether Fermat's last theorem were true. So we want to find out what holds in the world, what are the laws that govern formal structures in the world. And this is what mathematics does. What logic does is it takes certain formal elements and certain formal principles, and it builds them into our language, and it uses them in order to conduct formal proofs, logical proofs. Now, just because of the formality of these proofs, they are necessary. They are force, they have a very strong modal force. But what logic does is use the formal in order to develop methods of reasoning. And what mathematics does is studying the formal. Now, logic and mathematics are still interconnected. That is, the way I think about it schematically, we start with some kind of very simple logic mathematics, maybe something like Boolean algebra. We can then develop a very simple theory of, say, sets, for example, naive set theory. Then we use it in order to formulate a more complicated logic, a more complex logic. That is the simple logic that we use, the Boolean structures. We use very simple logic, say sentential logic or Aristotelian logic, something like this. Then we have more knowledge about formal structures. We use it to develop something like Fregean logic, quantificational logic, predicate logic. Then we have this system. We use it to develop a more advanced mathematics, for example, axiomatic set theory. Once we have axiomatic set theory, we can develop other logics, for example, logic with generalized quantifiers of various kind. And so logic and mathematics work in tandem. This is part of my holistic approach, that things are connected to each other. They both deal with the formal, but they do different things with the formal. That's how I look at it.
I have the following question. I understand that the background of your concept of mathematical truth is the correspondence theory of truth. But the difference between mathematics and natural sciences, as I understand it. So in the case of natural sciences, we hold that our claims must correspond to some facts in the real world. Okay, now we have at least 3 different geometries which describe space in different ways. Euclidean geometry. So it's how Greeks understood their space. Then Lobachevsky geometry or Riemann geometry. So which of them corresponds to reality? So I don't quite understand the term correspondence you use in your talk. Thank you.
Yeah. For me, this is, again, this is an open question. This is, I think that originally people thought about the geometry of space as Euclidean because it reflects the way we experience space. And you have theories like Kant in which, you know, the Euclidean geometry is part of sort of the basic way in which we see reality. We couldn't see reality otherwise, and there's something in it. We cannot it's hard to imagine something that is not Euclidean. And, you know, there's a historical question of what was the relation between the conception of Euclidean geometry as applied to the physical world and as standing on its own. And then there were these developments that first on the abstract level, there was the question whether when you think of mathematics, as I described with respect to the higher reaches of set theory, there is a question, could in principle there be a geometry in which the parallel axiom would not hold? And people found a way to think about it in a way that there would. And then there was the question of Einstein in physics physicists coming up with theories according to which the geometry of physical space is not Euclidean but Riemannian, and then there is again, if we want to go back and to unify the application of geometry to the world and the idea of geometry, then to the best of our knowledge, we have to say today that geometry is not, the geometry of space is not Euclidean. And so there is still, I mean, you know, all theories could be mistaken, so it's possible that we will end up eventually with something else. But it is a question. There's a sort of, I think, an interplay between looking at geometry as just a model, just as an algebra, a way in which we can think or we could apply to the world, and thinking about what there really is in the world. And the question of how the world is a complicated question. It's not a question that the philosopher of truth can solve. And so that's how I will look at it.
The question about formal and informal. When we talk about the truth, we cannot speak only about formal things. And what is the combination of formal and informal? So when you talk about the formal properties of the physical world, do you imply some informal view on the application of formal methods? And in this case, do you see the necessity of ethical non-neutrality when we talk about truth? Truth as ethically non-neutral. And there is the possibility of combination of classical and unclassic logic in this case. So both formal and informal. The first question, and maybe the second, if you talk about the ethical non-neutrality, there is a good Russian proverb. For truth, there is just no price. For truth, there is just no price. And how do you see it from the mathematical point of view? Yeah.
Okay, so, well, first I would like to say that on the relation between the formal and the informal, this is something that I only started thinking about some time ago, but only recently developed a view on this. And this is what I will talk about in my talk in the Formal Epistemology Conference. I think that the key is invariance. I think that every property has a degree of invariance, and physical properties have lower degrees of invariance than formal properties. However, some physical properties still have a relatively high degree of invariance, and that's why there are laws of physics and not just accidental facts of physics. And so I think there is a structure that relates the different properties in the different fields in a somewhat systematic manner, and you can talk about it, you can study it. I think that this is a subject matter that really should be studied much more than it was studied now. I should say about what you said about logic that there's also, bivalent logic and classical and non-classical logic. For me, this is also a question of look and see. There's a fact of the matter. Take, for example, bivalent and trivalent logic, okay? We know that there were quantum mechanics physicists raised the idea of non-Boolean logic, non-bivalent logic. But if we just take bivalent and trivalent, the way I see it, how it's connected to the world, is the following. The way we think about the world now is that often in classical set theory, that the basic structure of properties is this. You have a domain, and each property divides the domain into two. The property or its extension in the domain and its complement. But it is in principle possible that each property divides the domain into three parts, not into two parts. And if this is the case, if this is how the properties in the world are, then we will have trivalent logic. And so for me, again, all these things are matters of discovery. It's not simple to discover these things, but it is a factual matter. How do properties behave? What is the basic structure of properties? It can be bivalent, it can be trivalent, it can be fuzzy, it can be many other things, but these are all targets of knowledge in my view.
But we discover something essentially new that teaches us, and ethically non-neutral teaches us. And for example, we are in the building of the School of Economics. My point is just for truth, there is no price. We can comprehend it when you talk about E, we go beyond the continuum hypothesis. So the truth doesn't expect price for itself.
Yeah.
And we find something new, essential and new in this.
Right. In economics has a certain view of what is important to human beings and what they care about. And I think that the view of human beings from philosophy, or at least from my philosophical point of view, is somewhat different. And I think that from my point of view, to be human, a very important part of being humans is having a set of values. And I think truth is one of our values. Now, truth may not be the kind of value that economists recognize as having a price, but I think it is very basic to humanity.
But it means that this value in brackets that can be valued for truth, there is price. We cannot just put some value against it, so it will be wrong. So Nietzsche, you remember Heidegger, Nietzsche, they valued everything. And
Yeah.
They valued the man, the price of the man.
Right.
So when you talk about the truth, we cannot price man. We cannot give value to a man. in
Right,
that sense.
right.
And this will be ethical, not neutral.
That's
And
right.
the mathematics teaches us that. When we think informally about mathematics.
Yeah.
Do you agree with that?
I don't know. I think we have to talk about this more so that I'll be clearer about exactly what you mean and how I think about it.
Okay, thanks. The next question.
My question is about the following. In the middle of your presentation, you're mentioning the concept of numerability. And my question is there any necessity to distinguish numerability and countability as such in the realm of your philosophy? Thank you.
Numerability and countability?
Yes, exactly.
Well, I tend to think that there is, because I think of cardinalities as associated with numerability, and I think of cardinalities as going beyond the countable. So I would say, at least in the way that I'm thinking about mathematics, Yes, there is. However, again, I could be wrong and about this. So this is, I would treat it a little bit more as, you know, a detailed in the whole approach rather than sort of a general principle of the approach. But if we accept, according to the line of reasoning that I presented, that in order to understand the formal laws in full generality, we have first to get to the countable and then to get to the uncountable, then numerability will have to extend to the uncountable.
Can we extract some interesting mathematical consequences from your approach?
No, I did extract some consequences from my approach in logic in the direction of generalized quantifiers and things of this kind, but I have not really worked on the mathematical ramification of this approach. I actually would be very interested to hear if people have any ideas about that.
Thanks. Can we look once more to the slide about L?
About what?
About L. V equals L.
Which one is that?
V equals L.
B equals A. V equals L. V equals L. Okay, sorry, I'm very sorry. Okay, let's see.
Yes.
What do you say about the mathematical games and economical games?
Ontology, you know, no. This? Okay. Yeah. Yeah.
By beyond L, do you mean the consistency strength or just the existence of non-constructible reals or something?
The non-constructible cardinality, and it's a question really how to look philosophically at this level of set theory. So I think that philosophically it's easy to at least for my approach, to understand set theory up to L. But once we go beyond it, I think there are various options, and this is something I hope to think about more. As I mentioned one thing, I think that some people say that the solution to the continuum hypothesis might require understanding of results from higher cardinalities. So if this is the case, that will actually have relations to cardinalities below L. But another way in which one can look at set theory above L is to say, well, if we want to think about all the possible collections of objects that there is no reason why there shouldn't be collections that exceed L. And so these are two ways in which I can think about it, but there may be other ways of thinking about it.
What's your personal opinion about V equals L?
I have an opinion. I feel that this is a question for mathematicians
Your
to
approach
solve.
doesn't lead to any solution.
Not as far as I'm aware of. Maybe if I could think more about it, or me or someone else might find that it has results, but not as far as I have developed it.
Thank you.
If you please, what do you think about the mathematical games and economical games in particular? It's were absent in antique times, and does it present the truth in mathematical and economical games?
This is an interesting question. I'm not very knowledgeable about it, but I will tell you how I think about it. I think about it somewhat in the way that I think about questions in philosophy of science today. There are many philosophers of science, including my colleagues, some of my colleagues, who think that idealization is falsification. And I don't agree with it. I think of idealization is, again, something like an Aristotelian view of idealization. You take a certain aspect of reality and you remove many things that are not related and you get to an idealization. And I tend to think about economic games, game theory, in this way. So game theory, I think, can be models of actual situations, and some results can be true about actual situations, but and maybe some games are more like algebraic models, things that could be applied to actual situations. But as far as I'm concerned, the fact that games abstract or remove or idealize for many aspects of actual situations does not mean that they are not true or that they do not apply to reality. This is my very general approach to the idea of games.
And in the framework of your concept, do we live in metrics? And if it is so, where is live the genuine, unique truth in our reality within the matrix or in super hyper computer of higher powers?
This is the kind of question that as a philosopher of truth, I don't have an answer to. I think that this is a question for specialists in this area to think about and to find out. And I think what they will find out might relate in various ways to what I'm thinking about, but it's not something that I thought about or that I think my approach has direct consequences for.
In matrix concept, all resources are finite, as in your concept. And what do you think about that?
Say it
In
again.
matrix concept, the resources are finite. And in your concept of truth and reality, all is finite, as I understand you right.
Yeah, I think that on my view,
And what is the correspondence?
I don't think that correspondence requires finiteness. I think that correspondence allows us to go beyond the finite, and I think that as in the case of mathematics, I think we should affirm the infinity of cardinalities and infinite structures because they represent something that holds of reality, even though in reality you don't have to have infinitely many objects or individuals or something of this kind.
Do you believe in actual infinity?
Again, you need to I need to understand better what actual means here. I think that the way I present my theory offers or requires a critical re-examination of actuality. People use actual in many ways, and I think that in the way that I'm thinking about truth, I think that the distinction between actual and non-actual. The non-actual is real in some sense, in the sense that it enables us to understand the laws that govern what is actual. But I think that many people look at actuality in many ways, so I think it requires a real examination of the notion of actuality.
Thank you.
So your talk was about mathematical truth. And in mathematics, and in particular in mathematical logic, there is a clear distinction between truth and provability. And so it is not quite clear what is the role of the axiomatic method. Why do we need to pursue the truth through deriving it from axioms? Why do we need to put forward some axioms? And for example, if someone proves some property of spaceship engines from the continuum hypothesis, do we really think that this property really holds for engines and spaceships will fly as we expect them? Or this is just a mathematical game of deriving something new, strings of symbols from other strings of symbols? So any relationship of these to the axiomatic method and the provability?
So first, I don't think of proof just as a game of symbols. The way I think about proofs is proofs in logic as follows. I think that the semantics of logic, the model theory of logic, is an attempt to describe a formal. It is based on formal principles, formal laws that govern properties in the world in terms of truth. And but I think that because human mind is limited, we are incapable in many cases to draw consequences, actual consequences, just in terms of truth. So formal law, so laws of proof are laws that enable us finite beings to practically apply consequences which are expressed model theoretically. Now, we know that once we go beyond very simple logics or some logics, we have to have truth in addition to proof. Truth is not reducible to proof, but an adequate system of proof has to be sound, so it has to agree with truth. And so that is how I generally see proof, and I see its significance. I see proof as grounded in truth, but proof is only a partial representation of truth. And it's very important for humans, very useful, but it does not exhaust the notion of what follows from what.
Okay, two last questions, please.
Small question about truth. Is it possible that there is a truth that cannot be proved, or cannot be, so, or we cannot observe that it's, or prove that it's really truth? So, yeah, is it possible? Is it possible for truth to exist without any way how we can prove it?
Yes, I think I tend to think that yes, and yeah.
Okay, and the last question, Mikhail. Just a minute.
Why not to say just that structures are individuals that can recur in various substrates? And would you call this view Platonic or Aristotelian?
Platonic or Aristotelian. I tend to think that it's not. Well, I can see, I mean, one can look at it in this way, because on the one hand, we are starting from an Aristotelian conception of reality, and on the other hand, we say that once we take away parts of it, the formal parts, in order to describe them, we use structures with individuals, and that gives a certain reality to the individuals, representational reality. So I can see how someone might want to say that this is Platonistic Aristotelianism. It's not something that occurred to me, but one has to be careful to distinguish it from the kind of Platonism where you think that there are sort of two realities, one Platonic reality and one actual reality, real reality, and there is a problem of how to connect between them. I think it's not Platonist in this way, but it is Platonist in the sense that there is a certain reality to the individuals that we introduce as posits. They are not just games, they are not just conventions, they have to be systematically related to something in the world.
Okay, thank you for your talk and thank you for discussion. We will be glad to see you tomorrow at 4:40.